Hello and welcome to FLUXANA Laboratory. I will be your host today for the next 30 minutes probably. My name is Konstantin Brenkens and today's topic, as you can see on your screen, will be pressed pellet versus fused beads. And what we try to do is to help you decide in the future which of the two preparations to use for your applications in the end. We will go through a rather short presentation, and then afterwards, if we still have some time left, we will answer some questions. So feel free to use the questions and answer dialogue in your menu to just write some questions. And then in the end, we'll pick some of those and answer them live, or we will come back to it later via email. All right, so let's get started. As I said, today's topic is the two preparation methods of pressed powder or pressed pellets, as they are called, versus fused bead done with a fusion machine. And we will start by comparing the two processes. So to give you a little idea on how to prepare a pressed pellet and how to prepare a fused bead. We will talk about the final shape of the samples, or rather the preparation, and what influences are there that are important for the analysis in terms of results. And finally, we will look at some examples when to do a pressed pellet application and when to do a fused bead. And hopefully this will help you to make that decision in the future for any given applications you want to do in your laboratory. So we'll start with pressed pellets. So we have a few characteristics here, which are also goals basically that we want to achieve with a good pressed pellet. So first of all, we want to have it stable. It should not dust or powder away when we are handling it or when we are putting it in the X-ray spectrometer. It should also have a defined density and no air inside, which helps us with the accuracy in the end. The advantages of this means it does not contaminate the X-ray device. So we don't want the powder to stay inside our measurement chamber. Modern spectrometers nowadays do have some safeties installed, but of course, it's always better to have a sample that comes out of the X-ray the same way it goes in, and it doesn't leave any, unwanted residue behind. In terms of durability, pressed powders are usually meant to only last for one or maybe a repeated measurement, but in general, we want them to be stable or durable enough to just do the analysis and basically throw them away afterwards or on the next day. Procedure-wise, there are multiple ways to do a pressed pellet. The easiest one, obviously, is just direct pressing. We take our powder, we put it in the press, and we have a pressed pellet afterwards. That, of course, only works with samples that bind by themselves. Another way to do it is to use these alumina cups to help with stability. Basically, we take the powder and we press it into these alumina cups. This gives them some mechanical stability and also allows us to put a label on top or to just write a name. And it also improves the ability of auto-samplers to handle pressed pellets. Usually with direct pressing, it's a bit rough for most auto-samplers, but if you have these alumina cups where you press them in, that usually works fine. Another example is pressing your powder into these rings. These are mostly for automatic laboratories, where these rings again help to transport the sample from preparation station to measurement station and so on. this is kind of the same idea as an aluminum cup, with the added benefits that these rings can be used multiple times. You simply clean them afterwards, and then you do the next one. If you have a sample that does not bind of its own, you want to introduce a binding agent that helps with that. And in this case, we have the little press pellet help pills, I think it's what they're called. We have a little table here to give you an idea what binders are available. The typical one that is used most of the time is simply wax, or in FLUXANA terms, it's called Cereox. Basically, this is a very clean wax that is a good binder, and we don't have any chemical impurities that we add to our sample. So it's always a good first choice to try. It doesn't work with most automatics processes though, which in the end, it ends up clocking these automatic presses and so on. So it's more for laboratory use and not for automatic or routine uses. Another one is the Boreox, which is at the same time as being a binding agent, it also is a grinding aid. So you can combine your grinding process with the adding of a binder, and it stabilizes the sample. You can also use it for baking. We'll come to that in the next sheet. And it's the new replacement for boric acid. Boric acid used to be a quite common binder, but nowadays it's considered hazardous, so it's not used anymore. And these ones also come in tablets. That's what we saw on the picture before. It's basically, you get it as a powder or you get it as a tablet. The process is step by step pretty simple. You grind down your sample. At this step, you would also add your grinding aid or binder. You weigh the sample. If you didn't do the adding of the grinding aid binder here, you would add the binder next. You mix the sample and binder mixture, put it in your die, and then use an aluminum cup as an option. Or alternatively, if you do a direct press pellet, you can use pellet films to help with releasing. You pour that into the die, you make your pressed pellet, and as a result, hopefully you get like the perfect pressed pellet out of it, and that goes to the X-ray. A special case, if you have very small amounts of powder, let's say like below 0.5 gram of material, you can do this baking, where you basically use the Boreox as a filler, and you press a thin layer of your material on top to analyze then. That was press pellet. Quick overview for fuse bead. What do we want to achieve here? We want to have a perfectly homogeneous sample with no particle inclusions and no crystallization effects. And a big advantage over the pressed pellet is that these are a lot more durable in terms of storage. Like you can prepare a fused bead and use it, let's say, for half a year or even longer, depending on the recipe that you were using. These samples, they will change over time, but very slowly. So they are a lot more durable than when you compare it to a pressed pellet. The process for fused bead is schematically, it's like this. You take your sample, you take your lithium teptaborate, which it's also called flux. You put that into, you homogenize it, you take the mixture into a crucible. Usually these are made out of platinum. Then you do your fusion, and the result is a fused bead. There are different types of fusion machines that are still used nowadays. The easiest and oldest one is simply manual fusion in a muffle furnace. That involves a person doing all the work in front of an open muffle furnace, doing the agitating manually and so on. Those have been replaced mostly with automatic fusion machines now. Also, they come as muffle furnaces. For example, we have the Vitriox Electric here. And there is also some models using induction furnaces. And last but not least, these are the actual older machines, which are gas-operated fusion machines. For example, the Vitriox gas. Basically, we are talking about an open flame here that you put your crucible on top, and he does the fusion and the pouring later automatically. Those are run by propane, butane, natural gas. I think we don't need to go into the details too much here, but they are quite common nowadays. In terms of programming, obviously, if you do it manually, you would have your own process. But one of the big advantages of the automatic machines is that they do it very repeatedly. And we have an example here of one of our fusion programs, which is the cement applications. That what we call is basically the fusion process is divided into 4 steps of fusion and then an additional cooling time. And for each of these steps, we kind of control the temperature. Then after this main fusion 2, he does the pouring, and then he has the cooling cycle, and afterwards you can take off the fused bead. So total is around 1080 seconds, which is like 10 minutes and something. From putting in the sample and taking out your fused bead for measurement. Now, when we compare both these preparations method, we can already sort of say that the advantages of pressed pellet is that it's fast, cheap, but less durable than a fused bead. In terms of fused beads, what we are talking about is we need more time to prepare a sample. It is more expensive due to the materials involved, and we get a sample that has a longer durability. But still, why would we spend more time and money to do a fused bead preparation? What is the benefit of it? So in order to answer that, we will have to look a bit about the actual situation in analyzers now. So we're moving away from the preparation now and going to the X-ray. And on this sheet, we have like this, we see a picture of the, let's say this is our sample in our spectrometer. So we have the X-ray tube exciting it with the X-rays. And then we have the fluorescence happening inside the sample going out to the detector. And one of the important things is always the question, how much do we actually see of our sample in terms of fluorescence signal reaching the detector? And the question is, what is the analyzed layer of our sample? And you can already see here, it's indicating that it's rather slow, and we have some more numbers here to back this up. So you see the analyzed layer is mostly depending on the energy of the line that we are measuring. And secondly, on the matrix, the rest of the sample that we are measuring in. And this table is just an example. We'll just go to the next where we will highlight. And I think silica will be a good thing to have a look on. So let's say we measure our silica Ka alpha, and we measure it in a graphite sample. So it's basically carbon as a rest. Then our analyzed layer would be 72 micrometers. So we're going quite deep into the sample, basically. But as you can see now that the matrix gets heavier, going to silica and iron, our analyzed layer gets smaller and smaller. So basically what we are analyzing in an iron matrix is only surface level. We are only analyzing the first few layers of the sample. And that is an explanation for some of the effects we'll talk about later. As you can see now, when we go higher in the atomic number, the energy gets higher as well. And so our analyzed layer also gets bigger in the end, up to a point that if you're looking at zircon Ka alpha, we have to make sure that our sample in a graphite sample has to be like 5 centimeters thick. Otherwise, we are actually measuring something behind the sample. And well, the software can do like a thickness correction for all of that, but it makes it a bit more complicated. It's one of the reasons you usually would go for an L alpha or L beta line here, or even maybe a K beta of zirconium to avoid this problem. Some more numbers here. Again, let's focus on the silica. This is an example of an actual standard that we prepared. This is a dolomite standard, and we did a pressed pellet, and we had a look about how deep do we actually measure. And when we're looking at silica, we have the concentration of the sample here. It does not matter right now. This is the energy, but what is important for us is that the amount of sample we actually measure is only 13 micrometers. And taking into consideration that the average particle size of your samples is usually, well, it says 40 to 150 micrometers here. Let's say one of the usual numbers I always see is below 50 microns. That's something like you can sieve that in terms of your sample when you take the fine particle, the fine participations. That's a lot. Like the particles are actually bigger than what you're analyzing. So what we're seeing is this. Wieso kann ich jetzt nicht weitergehen? Ah, there we go. Sorry, there was a little lag. So what we're seeing in our analysis is sort of this effect here. Depending on the particle sizes and their distribution in your sample, when it comes to a pressed pellet, it is very important how they are distributed, because we are actually in some case only analyzing the topmost layer of our particles. So this is what is usually referred to as particle size effects. So you have to be very aware of that depending on your analytical elements and the way you prepare your samples, you might just be measuring literally on the surface of your sample. And I think this is the comparison now. If we look at the pressed pellet, we have this way, this kind of situation. We have a not perfectly flat surface, and we have these particle size effects, and we are only measuring on the surface. So that is a problem analytical wise, while in the fuse speed, we can claim that this is a perfectly homogeneous sample. So by dissolving our sample into the tetraboroid, we basically eliminated all of these effects, and they don't show anymore. They don't have any effect anymore. So in the end, it comes down to this. We have the comparison here. We did the same calibration for silica in this case, and the left side is the pressed pellet, the right side is the fused bead. So it's the same samples, the same standards. And if you just look at the standard deviation of the curve, the fused bead is like roughly 5 times better, even though the recipe is like highly diluted here. This would be 5 + 1, so more sample than binder. And this would be 1 + 8, so a lot more tetraborate than sample. But since we destroy the matrix, we get a better standard deviation. And usually, like this is an indicator of the quality, and you can think of it as a plus minus. Basically, every analysis you would do on these curve has to be plus minus the standard deviation behind the results you get. And to sort of emphasize on this a bit, we'll talk about some actual examples on how to use the two preparations in the field. So let's say we want to analyze a geosample or samples with volatile elements, and we want to precisely determine the main components. Mostly what is used is the pressed pellet. And there is an example here. This is the sample name is silty soil, so it's like a geo standard. And we prepared it with a fuse bead. Again, we have 1 gram of sample plus 8 gram of tetraborate. And we took the same sample as a pressed pellet, where we took 4 grams of sample and 1 gram of the Seriox. And if we look at the results, I think this was done, the measurement was done with a standardless software. So what we are seeing here is the oxide concentration, and the number next to it is the estimated error. The software we are using calculates this error based on the signal and background. And in a geosample, due to the high dilution, the pressed pellet actually like the results for nickel, for example, are very similar. But if you look at the estimated area on the fused beads, it's a lot higher than on the pressed pellet. The reason here being we are using a more concentrated sample when we do the pressed pellet, and in the fused bead we do a high dilution. Similarly, on these other elements, we have rubidium, strontium, and yttrium here. We do see something, well, strontium and yttrium we don't, because we have such a high error of the message. And then he says the error is higher than the result, so I'm not reporting it. And again, on our concentrated sample, we see actual concentration results with a very small error attached to it. Because we have a more concentrated sample, we are able to get better results on the pressed pellet here. Sulfur, being a volatile element, displays the same pattern. In fusion, we are talking about a high temperature process. So volatile elements like sulfur, for example, they simply disappear. So when you do a fusion, you don't find the sulfur in your sample later because it's gone, while in the pressed pellet, you can still find and quantify it. Another explanation, or another example where we use the fused bead would be when you're going for metal alloys or ore testing, and in general quality control with very tight specification. I think metal ores is probably the best example here, because the ores are bought in bulk, like we're talking thousands of tons here in a shipment, and you pay according to the iron content, for example. And with these large amounts, it matters if there is 0.5% more iron oxide or less, because on the big amount, it's a lot of money. So as an example here, I would like your attention on the left side here. This is an example of quality control of cement, and it is done with fused beads. And on the left, we see a table here where we have one of our CRMs. We have the target certified values, and we also have a validation target. Basically, this is the accuracy that we want to achieve. And we have multiple preparations here. Like in this case, it was 6. And then we have the mean, standard deviation, and the bias. And coming back to silica, which has been our example this whole time, if we look at this, I just have to get my picture out of the way here. So we have our target and we have the allowed offset, so to say. And in this case, we are right on the target. Our results have a bias of 0.01, which is fine. Our allowed bias would be 0.15. And if we now go back to we've seen this picture before, the standard deviation of our curve. Looking at the pressed pellet, the standard deviation doesn't even match this. Like the standard deviation of our curve, which is the average offset, so to say, it's larger than our validation target. So it's not guaranteed to actually achieve this with the pressed pellet, while in the standard deviation of the fused bead, 0.10, we're below, and you can see that it's repeatable and we are matching our targets. So in summary, when the accuracy or the correctness of the analysis is important, usually what you go for is the fused bead preparation. And yeah, I think this is already the last picture, so we will have some time for questions after this. So when it comes to the summary, to answer the question, what do I use for my given application? It's always sort of a balance between the time and costs and the needed accuracy. Pressed pellet is very good when you have to have quick results to, for example, control a process, when you need to know what kind of raw material do I need to add to my my process in order to get the good final result, like in a cement plant, for example. It also has some advantages when it comes to volatile element and some trace analysis, because we are using a more concentrated sample. On the other hand, when you want to do a quality control, a reference method, when we're talking about the ore testing, for example, and your main target is the accuracy, then you would usually go for a fused bead, because the step of eliminating your matrix and getting rid of these particle size effects has a big influence in the repeatability and accuracy of the analysis in total. So that was the quick journey. We still have a few minutes. I just would like to do a little advertising break here and remind you of the next episode of FLUXANA Laboratory. And I think the next date is in December, and the topic will be different fluxes used in fusion. So yeah, just something, if you're interested, we will be happy if you join us. And I'm just going to switch over to the question now and have a real quick look at this. So let me just see. We have one question here about the crucibles used in fusion. Is if there are other options. Yes, they are. Platinum is the mostly used one, but there are other options. For example, the electrical machine we use has a silica oxide disposable crucible. It's a one-time use only, but for example, it's used in catalyzed analysis, where platinum is an analyte of your method. And of course, if you want to analyze platinum, you can't do a fusion in a platinum vessel. It doesn't work. So there is a silica option there. There is also a zirconium one for what is called peroxide fusion. So platinum is the most common one, but there are some alternatives. If you want to have some more details, feel free to write, and we'll just get to that, back to that on email. The best way to, next question would be, is the best way to prevent volatiles from escaping? You can always work in a closed environment. So simply putting a lid on your crucible helps a lot. You just want to kind of try it. The volatilization still happens, but you can minimize it by simply putting a lid, and then best work in a closed system like an electrical furnace. This one is too long to read. I'll come to that one later. We'll cover that by email. Let me see. There is another question here. Is it necessary to mix sample and flux before fusion? It's not necessary, but it helps. The actual homogenization takes part when your fusion and sample mixture is liquid. So each fusion machine has a sort of rotation device. And so the real mixing happens when everything is liquid. In practice, we always mix the powders before. But it's more like when I do the balancing, I put everything in my crucible, and then I simply take a spatula, or you can even use like a wooden stick if you don't want to contaminate anything with the iron from the spatula. You simply stir it a bit, like 2-3 times, just to mix it roughly, and then it goes on the fusion machine. There is another question about the error effect of weighting. Well, that mostly depends on your balance, basically. As a rule of thumb, in our lab, we do have like analytical balance that we use for these, and we use them for pressed pellet and for fusion as well. When we're doing the mixtures for pressed pellets, we take 2 digits on the analytical balance. So my recipe would be 5.00 plus 1.00 for a pressed pellet. In a fused bead, we do 4 digits. The reason being because of error transmutation, basically. We use 4 digits for balancing, and then on our reports, we would only do 3 digits we would put on our reports. So the one is sort of your reserve. So if you have analytical balance, especially in fusion, it's always helpful to keep to a standard recipe and don't allow too much tolerance in balancing. Gas and electric, short comparison. A few words. Gas is old, quick, and very robust and reliable, but also dangerous. Electrical is a bit more expensive, takes longer, but it only needs a power socket. And safety-wise, there is a lot more regulation in the modern electrical machines in terms of self-regulation. There is a lot more of safeties involved. So I would say that gas is definitely a good choice for a heavy duty environment, like a lab in an industrial plant. But there are some dangers, like open flames and all that, and you need more consumables. Electrical machine is more laboratory environment because it's more it's more affected by dust and all that. But in the other hand, you have more control over the whole process in terms of regulation and such. And I'm sorry, we are already at the end of our 30 minutes. So there are a few more questions. There's been a lot of feedback. Thank you for that to start off, but we will not be able to address all of this. We will come back to this by email though. All of your questions have been noted. They're in the system, and we'll simply write you an email as an answer. And of course, feel free to contact us with any feedback or other question regarding this little seminar. And with that, I would like to thank you for your attention. And yeah, hopefully see you next time. And goodbye. Have a nice day.